Hello, and welcome to my video series on algorithms. This is part 1 of Module 6, Dynamic Programming. In this video, we will introduce the fundamental concepts of dynamic programming. Dynamic programming is a powerful optimization technique with significant applications in various fields, such as in economics, automation, and computational biology. This method was developed by Dr. Richard Bellman in the 1950s. In the field of algorithms, dynamic programming is often used to improve the time complexity of recursive algorithms. Essentially, for a problem that can be solved using recursion, if it satisfies certain conditions, we can use dynamic programming to make it run more efficiently than naive recursion. However, if the problem does not meet these conditions, it cannot be optimized using dynamic programming. We will specify the conditions later in this video. For the remainder of this video, we will refer to dynamic programming as DP for short. In general, DP describes a strategy to optimize an object function. It involves making decisions at a series of time points by considering the current and past situations. As shown in the figure, at time point ti, DP attempts to decide the best action to maximize the object function by considering the options available at ti and what has been achieved at ti-1. For example, imagine a real-life scenario where we want to maximize our wealth. DP helps you to create a plan by evaluating the possible ways to grow your wealth, along with the amount of money you currently have. Here, the possible ways to grow your wealth corresponds to the options available at ti, while the money you already have corresponds to the object function value achieved at ti-1. Note that the dependency of ti is not restricted to only ti-1. It can depend on multiple states at any previous time points, but it cannot depend on the future. In the context of recursive algorithms, we treat the subproblem as analogous to time points. Even though subproblems are discrete, while the time points are continuous, the same idea of DP still applies. In this figure, the subproblem Pi corresponds to a larger subproblem whose solution needs to be constructed from the solution of the smaller subproblem Pi-1. Of course, the dependency is not unique either. That is, the solution of the subproblem Pi can depend on many smaller subproblems, but it cannot depend on any larger subproblem. Now we have understood the basic idea of DP, we shall discuss where does the name dynamic programming come from to deepen our understanding. From the autobiography by Dr. Bellman, Eye of the Hurricane, he described the reasons for choosing the name as follows. He used the word dynamic to mean multi-stage and time-varying, which corresponds to the feature of DP that it tries to optimize the object function stage by stage. He also used the word programming to mean planning, such as that from linear programming or integer programming. Note that it does not have anything to do with computer programming. Previously, we used the computation of the Fibonacci series to illustrate the concept of divide and conquer algorithms. We will again consider this problem in the context of dynamic programming. Recall that the Fibonacci series was originally used to model the population growth of rabbits in nature. The first two terms of the series are 1 and 1. Beyond this, the nth term is defined as the sum of the previous two terms. In other words, fn equals fn-1 plus fn-2. Recall the naive recursive algorithm we developed in part 1 of Module 5. Line 2 handles the boundary case, and line 3 corresponds to recursive calls. So, what is the time complexity of this recursive algorithm? Let's visualize this algorithm using the recursion tree shown in the slide. At the root, we are computing the value for fn. At the first layer, we are computing the values for fn-1 and fn-2, and so on. Observe that the indexes of the leftmost subproblems, which are colored red in the figure, decrease by 1 as we go one layer deeper. In this case, we can see that the recursion tree has n layers at most. Additionally, it is easy to see that the number of subproblems doubles as we go one layer deeper. As a result, there could be 2 to the power of I subproblems at the ith layer. Summing this up, the total number of subproblems to solve is in O 2 to the power of n. In other words, the overall time complexity of this algorithm is exponential. It might be surprising to find that solving such a simple problem requires exponential time. So let's figure out why. Observe that in the recursion tree, there are several subproblems that are solved multiple times. For example, the purple boxes highlight 2 instances of the subproblem fn-2, while the pink boxes highlight 2 for fn-3. It is not hard to infer that fn-2 and fn-3 are not the only redundant subproblems in the entire recursion tree. We call the recurrent and redundant subproblems overlapping subproblems. Note that not all recursive algorithms have overlapping subproblems. For example, in the merge sort algorithm, we never sort the same set of numbers multiple times. Thus, every subproblem of merge sort is unique, and there are no overlapping subproblems. So, can we avoid unnecessary recomputation of these overlapping subproblems? Yes, the idea is to solve the subproblem when it is first encountered, and memorize the result for future use. For example, the green subproblem fn-2 in the second layer will be encountered before the blue one in the first layer. In this case, when we first encounter the green subproblem, we know it is unsolved, and we solve it as usual. Once we obtain the result, we memorize it by storing it in a table. Then, when we encounter the blue subproblem, we know that it has already been solved before, so we can look up the table and directly use the result. In this case, we don't need to go deeper with the recursion. The entire subtree rooted at the blue subproblem can be pruned, saving a lot of computations. This strategy is called memorization. Okay, now let's sort out the details of how to memorize the intermediate results of the subproblems. We know that the subproblems are indexed by its parameter I, which means that given a specific value of I, the corresponding subproblem is unique. Therefore, we can assign an array A to store the results of the subproblems. For example, in entry AI, we store the result for the subproblem Fi. The data structure used for the memorization purpose, usually an array or a matrix, is called the DP table. Note that the original problem Fn is also represented in the array A. Therefore, if we can fill up the array, particularly finding the value for the entry An, we can solve the problem. Now, we need to specify the way to fill the array. That is, we need to determine which entries to fill first and which to fill later. The principle for determining the table filling order is to ensure that when computing a problem, all of its dependent subproblems have already been solved. As a result, the filling order should be derived from the recursion relation. In our case, the recursion Fn equals Fn-1 plus Fn-2 indicates that computing the value for any entry requires its previous 2 entries. Hence, we can simply fill in the values from left to right. This way, we can ensure that when computing any fi, the results for its dependent subproblems fi-1 and fi-2 are available. Of course, the first two entries of the array should both be 1, as specified by the definition of the Fibonacci series. Thus, we will construct an array of size n and fill it up from left to right. The first n terms of the Fibonacci series can then be retrieved from the DP table A. Here is the pseudocode for computing the Fibonacci series using DP. Lines 3 to 5 correspond to the step of filling up the DP table from left to right. Clearly, this DP-based algorithm runs in linear time, which is much faster than the exponential time of the naive recursion. The speed improvement illustrates the power of memorization. Avoiding redundant subproblem computation can lead to a significant speed up. Now, we can summarize the main steps of a DP algorithm. First, we need to order the subproblems. This means specifying which subproblems each problem depends on. The dependency relation should be able to be modeled as a theoretic acyclic graph. Formally, we should partially order the subproblems, ensuring the relation is antisymmetric and transitive. Specifically, for any two subproblems I and j, antisymmetry means that if solving I depends on j and solving j depends on I, then I and j must be the same problem. This ensures unidirectional dependency between subproblems and prevents mutual dependency. Regarding transitivity, given three subproblems I, j, and k, if solving k depends on j and solving j depends on I, then solving k depends on I. With transitivity, we can eliminate cycles in the dependency relation. Both constraints together ensure that the subproblem dependency relations form a theoretic acyclic graph, which contains no deadlock and makes the original problem solvable using recursion. The second step is to write the recursive function, which characterizes the strategy we take to optimize the object function. Usually, the recursion function is written to express how a larger problem can be solved using solutions to smaller subproblems. Subproblems in higher levels of the recursion tree is therefore written on the left-hand side of the equation, while those in lower levels are written at the right-hand side. Therefore, we call this step top-down recursion. In our example, this step corresponds to writing the recursive function fn equals fn-1 plus fn-2. The last step is to solve the recursion by filling up the DP table. When filling up the DP table, we first solve the smaller problems that reside at the lower levels of the recursion tree. For example, when filling up the array for the Fibonacci series from left to right, the first two values we fill are f0 and f1, which correspond to the leaves of the recursion tree. In this view, DP table entries that correspond to the subproblems at the lower levels are filled first, followed by those at the higher levels. Therefore, we call this step bottom-up tabulation. As a result, we can summarize a DP algorithm into three main steps. The first step is subproblem partial ordering, which specifies the dependency among subproblems. The second step is top-down recursion, which describes the optimization strategy as the recursive function. The third step is bottom-up tabulation, which solves the problem by filling up the DP table. Lastly, let's answer the question raised at the beginning of this video. Which conditions should a problem satisfy to be solvable using DP? The first condition is that the problem must have overlapping subproblems in its recursion relation. The second condition comes from a critical hidden assumption we adopted when using DP. The assumption is that the memorized subproblem solutions are sufficient to reconstruct the solution to the larger subproblem. In other words, the optimal or correct solutions of the subproblems must be sufficient to solve the larger problem. We need this assumption because we can only memorize a limited number of solutions to each subproblem, usually the optimal one. However, if the solution to the larger problem requires suboptimal solutions of the subproblems, the required information will not be memorized in the DP table, and therefore we cannot solve the larger problem. In the Fibonacci series example, the assumption indicates that if fn-1 and fn-2 are correctly computed, then fn can be correctly computed as well. This property is called optimal substructure or subproblem optimality. Note that the optimal substructure is a somewhat strong assumption, and not every problem has it. Again, consider the problem of maximizing one's wealth. The optimal substructure property implies that you can achieve maximum wealth in year I if you achieve maximum wealth in year I-1. This is not necessarily true. For instance, in year I-1, you might spend money on learning a new skill or investing in a new business, leading to less overall wealth and a suboptimal solution for that year. However, the suboptimal solution at year I-1 could lead to the maximized wealth at the next year I. Taken together, the problem needs to satisfy two conditions in order to be solved using DP. First, it should contain overlapping subproblems in its recursion relation. Second, it should have the optimal substructure. In summary, we have discussed the general idea of DP in this video. DP is a technique to improve naive recursion. Given a problem, we can likely solve it using DP if it has overlapping subproblems and an optimal substructure. Finally, a DP algorithm usually contains three main steps. They are subproblem partial ordering, top-down recursion, and bottom-up tabulation. The topics we plan to discuss in this module include weighted interval scheduling, the knapsack problem, sequence alignment, RNA secondary structure alignment, subset sum, segmented least square, and the shortest path problem with negative weights. Thank you for watching, and see you next time.